In this video, we'll look at how we can change variables in multiple integrals. So recall from single variable calculus how you used substitution to introduce a new variable instead of x and make an integral easier to evaluate. We want to do the same thing for double and triple integrals, introduce new variables instead of x, y, and perhaps z to make these double and triple integrals easier to evaluate. And we've already done this in some special cases. For example, in 2D, we looked at polar coordinates, and in 3D, we had cylindrical and spherical coordinates. But now we want to do this in a much more general setting. So let me start with the two variable case and tell you what it really means is you have a new pair of variables, uv, and they are related to the old variables x, y by some transformation t, which transforms the uv plane and everything in it to the xy plane. What it means in practice is x can be expressed in terms of u and v, and so can y. So these you can think of as x being a function of u and v and y being a function of u and v. So let me just take these two functions and put them in a two-component vector, which I'll denote by r. So this vector r depends on u and v and has two components, x uv and y uv. Again, if you want to think of an example, just think of polar coordinates, and indeed let me just tell you about that example. So instead of the usual polar coordinates r and theta, I will use u and v. So x is now u times the cosine of v. So you can see that the role of r is played by u in this case, and the role of theta is played by v, which means that y will be u times the sine of v. And so if we look at a rectangle in the uv plane, so for example, let's take u to change between some constant values, let's say 3 and 5, and v to change between some other constant values, for example, pi over 6 and pi over 3, then this gives us a rectangle in the uv plane. Let me try and sketch that rectangle out. So this is the uv plane, and u changes between 3 and 5, v between pi over 6 and pi over 3. So then we are talking about this rectangle, okay? And we want to basically evaluate an integral over this rectangle in the uv plane. Now this transformation from uv to xy will take this rectangle and turn it into some shape in the xy plane. And this shape looks as follows. It is this polar rectangle, what we call the polar rectangle. And so when we define our double integral, what we do is we subdivide the u interval into small subintervals of size delta u, which means that our rectangle gets subdivided into these small strips, and then we subdivide the y interval, the v interval into small subintervals of a size delta v, which means that we obtain these small subrectangles in our initial rectangle in the uv plane. So this means subdividing the u interval means that we are subdividing in the sort of radial direction. It turns into this chopping up of that polar rectangle, and the subdivision of the v interval manifests itself in such a mesh in the xy plane. So let me just zoom in on this picture. So to look at one of these small sub-rectangles, polar sub-rectangles. So let me look at this one. Because what we want to do is figure out or approximate the area of this small polar subrectangle. So to do that, we just have to look at these corners and realize that if this is my vector r uv, and let's say that this rectangle corresponds to the vector r of uv, I mean that corner corresponds to r uv, then if I nudge in the u direction, which is the radial direction, by delta u, I get to that point, which is given by the vector r of u plus delta u v. Similarly, this corner right here is obtained from this one by shifting along the v coordinate by delta v. So that's r of u v plus delta v. Okay, and finally the fourth vertex is r u plus delta u v plus delta v. What I really need is these two sides. So the vector which points from this corner to that corner, that vector can be approximated by the it's the difference of these two vectors, but that can be approximated by the partial derivative of r with respect to u. So just and similarly for this vector, it's just the difference of these two vectors, but that can be approximated by the partial derivative of r with respect to v. So let me explain how that can be done. But remember that the partial derivative of r with respect to u is just the limit of this difference quotient r u plus delta u v minus r u v over delta u as delta u goes to 0. So this difference r u plus delta u v minus r u v is up there. So approximately that difference r u plus delta u v minus r u v is approximately r sub u times delta u. Okay, so let me put a box around this one. So that side of our polar subrectangle can be approximated by the u derivative of this vector r, which encodes the transformation from uv to xy. And similarly, the other side, for the same reason, can be approximated. So r u v plus delta v minus r u v can be approximated by the v partial derivative of u times delta v. Okay, and that gives us an approximation for the other side of this polar subrectangle. So now we want to find the area delta, let me call this delta A, the area of this polar subrectangle, or approximate it at least. So what that area is, well, the way we can approximate it, we can take these two vectors, r sub u times delta u and r sub v times delta v, and look at the parallelogram which they span and the area of that parallelogram. So, and what's the area of that parallelogram? So how can we approximate delta A? Well, it's the area of that parallelogram, which is the length of these two vectors multiplied by the sine of the angle between them. That's the formula for the area of a parallelogram. But if you look at that formula, that's basically just the length of the cross product of these two vectors. So really what we look at is the length of r sub u du cross r sub v delta v is what we need. So we can of course factor out those delta u delta v's, and what we have is the length of the cross product of r sub u and r sub v times delta u times delta v. So let's find the length of that cross product. For that we need these partial derivatives r sub u and r sub v. Remember, r u v is this vector, so r sub u is really just dx over du and dy over du. I'm just differentiating the components of r with respect to u. And similarly, r sub v is just the partial derivatives of the components of r with respect to now v. So dx over dv and dy over dv. Okay, so to think of this cross product, of course, we would need three-dimensional vectors. So let me just go ahead and add a third coordinate 0 to these vectors. So let's make them into three-dimensional vectors. Okay, so I'm just adding a third component 0 to each of these vectors. So I can talk about the cross product of r sub u and r sub v. And now if I want to compute the length of that cross product, what I'm really doing, remember what the cross product is, it's the determinant of the 3x3 matrix with I, j, and k in the first row. So these are the standard basis vectors in the first row. The components of u in the second row, so that's dx over du and dy over du and 0 in the second row. In the third row we have dx over d v and dy over d v and 0. So this is the determinant, which is the cross product of r sub u and r sub v, and we want to take the absolute value of that determinant. Okay, so if we evaluate this determinant, we want to take the length of that vector that we will get there. If we evaluate this determinant, you'll notice that it's only the k component which turns out to be non-zero. And what is that k component? So that it's just a 2x2 determinant, and it's going to be given by dx over du, dy over du, dx over dv, and dy over dv. So this is the 2x2 determinant, which is the third component. So it's the component multiplying the basis vector k. But now we have to take the length of this vector. K is a unit vector, so what we are left with is really the absolute value of the component of k, or the coefficient of k, which is just the absolute value of this determinant, dx over du, dy over du, dx over dv, dy over dv. So we have this 2x2 determinant, and we take its absolute value to get the length of that vector. Okay, so now we see that this small area, delta A, can be approximated by the absolute value of this 2x2 determinant times du dv. Okay, so this means that this absolute value of a determinant is what is correcting for that transformation from the uv to the xy plane and vice versa. So our integral formula for the double integral will take the following form. So it will turn into a double integral over some region R in the xy plane of some function f of xy. Will be expressed in terms of u and v as follows. We will take the double integral over the region in the uv plane, which is the pre-image of R under this transformation. And what we'll have is, of course, f of xy, but x and y depend on u and v, times the absolute value of this determinant. So let me just go ahead and denote this determinant dxy duv and take its absolute value. So this is the extra factor that we get here, is the xy duv absolute value, and then we integrate with respect to u and v. Okay, so this is our double integral formula in the new coordinates u and v. Okay, so since this 2 by 2 determinant and its absolute value was very important, what we do is we give it a name. So this 2 by 2 determinant is called the Jacobian of this transformation T. So let me just give you a definition. The Jacobian of T, which maps uv to xy, is the following 2 by 2 determinant. It is denoted as follows: dxy duv, and it's a 2 by 2 determinant of the elements of the matrix with elements dx over du, dy over du, dx over dv, and dy over dv. So this is the Jacobian. And as an example, let's compute the Jacobian of the following transformation. So a question for you is to take the coordinate transformation. So instead of x and y, we introduce u and v via the following formulas. X is u squared minus v squared, and y should be twice u times v. Okay, pause the video and compute the Jacobian below. Okay, I hope you pause the video and realize that the 2 by 2 determinant that we have to evaluate now is just obtained by differentiating these functions with respect to u and v. So if we differentiate x, this u squared minus v squared with respect to u, we get 2u. If we differentiate y with respect to u, we get 2v. So this is the first row of our determinant. If we differentiate x with respect to v, we get minus 2v, and if we differentiate y with respect to v, we get 2u. If you evaluate this determinant, you will get 2u squared, so that's 4u squared, and minus the product of the off-diagonal elements is minus 4v squared, but we have to subtract, so that's plus 4v squared, and that is the Jacobian of this transformation. For triple integrals, this story nicely generalizes, and there we, instead of uv, we have a third new variable uv, and let's call it w instead of x, y, and z. The same story generalizes, and what we end up with is a 3 by 3 determinant, also called the Jacobian, which contains the partial derivatives of x, y, and z with respect to u, v, and w in each of its rows, and that gives us the transformation from a triple integral in terms of x and y into a triple integral into u, v, and w. Okay, I hope you enjoyed this video, and I'll see you in the next one.